We're now ready to revisit our resistance. And so in particular, we're going to revisit our resistance with a non-uniform cross-section. And what I've said a couple times now and what we're going to see in this video is that our boundary value problem can help us figure out that resistance in the case of a non-uniform cross-section. So let's start with the general equation we had previously. So this was from a previous unit. Of course, we know that R is equal to V over I. And previously we had said, let's use an equation that relates V and E to say that this V is the line integral of our E dot dl. And let's use an equation that relates our I to our current density. And so I'm going to make a slight substitution, so it's going to be the surface integral. And instead of current density, I'm going to put sigma E, so essentially using our point form of Ohm's law, dot ds. So this was sort of our general equation we looked at in a previous unit. And again, let me just make a note here that I'm using J is equal to sigma times E. Okay, so how would we go about finding the resistance of a non-uniform cross-section conductor? So the first thing we want to do, as is usually the case, is to choose an appropriate coordinate system. My apologies. All right. And so depending on what type of symmetry we have in our system, that's going to dictate what's going to be the easiest to work with. So once we do that, we can assume some potential V naught between our terminals. So assume some voltage V naught as our potential difference between the terminals. So once we're assuming this V naught, that's essentially our boundary conditions. So now we can solve our Laplace equation. So we want to solve our Laplace's equation. So remember, our Laplace's equation was the case of a charge-free region, which we know our conductor is going to be, again, from previous arguments in previous units. So this Laplacian of V is equal to 0. And ultimately, when we solve that, we're going to get an expression for V. So once we have our expression for V, our fourth step is going to be to get our electric field expression. And then ultimately, we can get our current expression as well. So ultimately, we get our I from V, because remember, we said that our E is equal to negative gradient of V, so that's how we get our electric field from V. And then also we said that our I is equal to that surface integral of sigma E dot ds. So then once we have that, our fifth step to find R is to just say R equals V naught, that assumed voltage, divided by our current that we found from our voltage expression. So R is equal to V naught divided by I. And so again, this V naught is coming from our assumed potential V naught here, and our I expression is coming from the one that we found from our V equation from step 3. So there is an alternate approach here. So instead of assuming V in step 2, we could have assumed an I. So let me just note that. So an alternative is we could have assumed I naught in our second step. And so that just changes things slightly. We're still solving our Laplace equation, except now we're going to have an I naught. And ultimately, we're going to be solving for a V expression in our numerator. And we're going to be plugging that V expression over our I naught to get our R. So we're not going to have time, at least at the time of making this video, to go through any examples, but a good example of using this equation is example 6.8 in the textbook. So that's on page 256. And so if we find some extra time in class, we might go over that, but I would encourage you to at least take a look at that because using this technique to find our resistance of non-uniform cross-section materials is very powerful.